Okay, I've done a few sample problems from 4.1. In number 10, we had a picture, and we're supposed to look at this scatter diagram, see if there is any kind of linear relation that may exist, and if there is one, determine whether it's positive or negative association. And in graph number 10, it actually looked like this. It does look linear, and it is in the negative direction. In other words, as x gets bigger, y gets smaller, so that's negative. In number 18, we had to do the following. We had to take some data, and this was x and this was y, and what we had to do in here is draw a scatter diagram of the data. So in part A, I stuck this in list 1, I stuck these points in list 2, and then I did a stat plot. List 1, list 2, zoom stat, and my graph looked like this. Now keep in mind, I have to label it. Since this was just data and not pertaining to any kind of word problem, this would be x, this would be y, and there's my scatter plot. Part B asked to compute the correlation coefficient, which is the R value. So what I did is that we are going to do a two variable stats of list 1 and list 2 and get the sample data. So I found x bar and I found the standard deviation of x. I found y bar and the standard deviation of y. Now what I'm going to do, because I want to use this formula down here to compute my R value. This is what R equals. So what I did is list 1 is my x values, list 2 is my y values, and then in list 3 I did list 1 minus my mean divided by my standard deviation. In list 4 I did list 2 minus my mean divided by my standard deviation. And then list 5 I'm going to take and multiply list 3 and list 4. These are the formulas, okay? Now remember, this is just a z-score. So what I'm going to do here is I'm going to sum up list 5. So this means to sum up, this is the z-score for the x's, the z-score for the y's, and when I summed up list 5, I got negative 3.7336. Now to find my linear coefficient, I would take the sum of list 5 and divide it by n minus 1. So I take negative 3.73368 divided by 5 minus 1, and I get a negative correlation of negative 0.933. Part C says, is it a determine whether there is a linear relationship? And there is. I looked at my data, it goes down. I looked at my R value and it confirms that it's negative. And so with these two, I can say that there is a strong linear relation between x and y. So then I did example 22. It's talking about name the relation part 2. So for each of the following statements, explain whether you think the variables will have a positive correlation, a negative correlation, or no relation, and then support my opinion. There's no data, so it is just an opinion. So the number of cigarettes versus the baby's birth weight. Typically, based on what studies I remember reading about, that as the number of cigarettes go up, the baby's birth rate goes down, so there would be a negative correlation. Letter B says the years of education versus the annual salary. And we typically have said the more education you have, from a high school diploma up to a PhD, the higher your salary is. So it's a positive correlation. Part C talks about the number of doctors at a hospital versus the administrative staff. Now, if you have more doctors, you're going to need more administrative staff. So that's a positive correlation. Part E says the head circumference versus the IQ. Basically saying that if your head size is bigger, your IQ is bigger. And I don't think that has anything to do with it. So I would say there is no correlation. Part E says the number of moviegoers versus the ticket price. Well, if you have more people going to the movie, the ticket price should go down, and so it's a negative correlation. Kind of has to do with supply and demand. Now your opinions might be a little different, but that's what I was looking at. Okay, number 24 talks about the American black bears, and they tell you that a guy by the name of Dr. Pelton of the University of Tennessee did a long-term study of the population in the Great Smoky Mountains National Park. And one part of his study was to develop a model that could be used to predict a bear's weight, since it's not really practical to weigh the bears in the field. One variable thought to be related to weight is the length of the bear. And then there was a table of data which talked about length in centimeters and weight in kilograms. And so there's a bunch of lists there, 12 bears. And so what I did was I put in the list 1, I put the length, and in list 2, I put the weight. And you can see that table on page 204. Part A says, which variable is the explanatory variable based on the goals of the research? Now the goals of the research, you have to read the problem, actually says, let's see if we can predict weight based on the length. So the explanatory variable is going to be the length. Now to draw a scatter diagram, what I did is I put in list 1, list 2, and remember you do list 1, list 2, and you go up to stat plot, and you put zoom stat, and you get something that looks like this. Now again, weight, length, use the units, and include a scale and a title. Now determine the linear correlation coefficient between the weight and the height. So we're looking for the R value. Now we are going to do it by hand. You can do a linear regression and see if your R value comes the same way, but we're going to do the computational formula. It is one formula that, based on doing a two variable stats, all that information is there. So here's the formula. Now you would be given this formula, okay? So if you ever had to do it by hand, the formula would be given. Now when I do a two variable stats of list 1, list 2, this is the information that comes up. I have n equals 12, the sum of the x's is 17, 14, the sum of x squareds is this number, the sum of the y's, the sum of the y squares, and the sum of the x and the y's. This all is shown when you do a two variable stat. So basically I'm going to take this formula and plug everything in. So I plug everything in and make sure when you put it in your calculator that you actually put the parentheses in, and what you end up getting is approximately 0.704. So it asks, is there a linear relation? Well, the scatter plot looked kind of linear. The R is you've got a positive association because it's positive. It's not super strong, but it's there. And so I'm going to say, yes, there is a relation between height and a linear relationship between weight and height of the bear, and it looks positive. Now in 32, it tells us that we are going to look at the American black bear again, and they're going to say what happens if in problem 24 that I put in the wrong height. So let's say the height was really 141 and I put in 41 centimeters tall. So I have to redo the whole thing. So the height was and the weight, and now I'm going to put in 41. So now I find R again. This time I'm going to verify it with the calculator, but then do my work by hand. And then in 41 we find out, or in 32 we look at it and go, yeah, I found my R value, and it ends up being 0.254. And then I look at it and explain how the scatter diagram can be used to identify incorrectly entered data values. Well, the scatter plot looks pretty good, except it has one point out of the way. And so it looks like the 41 centimeters might be a bad one because it goes away from the rest of the data. So the R changes due to not being resistant. And that's one thing we wanted you to know. Now we could find R again with our calculator, where we would do a linear regression of list 1 and list 2. Now list number 33 has a lot of data in a table. You've got data set 1, data set 2, data set 3, and data set 4. So what they want us to do is first compute the linear correlation and draw a scatter diagram for each one of those. That means if I look at this data, I'm going to put in here list 1, list 2. I'm going to put in here list 3, list 4. I'm going to put in here list 5 and list 6. And then to do data set 4, we're going to have to erase some of them because I think our calculators will only do certain ones. We'll only go up to list 6. So I could actually put all this data in, and I would do a linear regression for each one of these. And then I would also draw a scatter diagram, and if the linear regression matches the scatter diagram, then I would conclude that it is linearly associated. And the reason we have to look at both of those is because you could have things that are related, but they may not be a linear relationship. So you need to look at both the scatter diagram and the scatter plots and your linear regressions in 33. What you are going to do is you're going to do a stat calc. You're going to do a line reg, and you'll do list 1 comma list 2. Since we're not going to necessarily draw it, then you can hit enter and it will come up with a R value. Now remember, if your R doesn't show up, you have to turn your diagnostics on. Now if you're going to do the data set for 2, everything's going to be the same, but this time you're going to do list 3 and list 4. The next time you're going to do list 5 and list 6, and you'll find the R values for each one of those. Now my calculator only has 6 lists, so I have to erase a set before I can do data set 4. By the Journal of the American Medical Association, researchers found that the length of time a mother breastfeeds is negatively associated with the likelihood a child is obese. In an interview, the head investigator stated it's not clear whether breast milk has obesity-preventing properties or the women who are breastfeeding are less likely to have obese kids because they are less likely to be obese themselves. So basically, looking at his statement, what might be wrong with concluding that breastfeeding prevents obesity? Well, he says it's unclear, so we can't conclude it. And it's probably because there's a lurking variable. For example, and this is just one possibility, nursing mothers may be more health conscious, and so their babies are less likely to be obese. And so that might be the lurking variable. And you get to